So, hello everybody, and welcome to the second We Brew With You live event, live from my living room. Really glad that all of you could join me today for this. So, today I'm going to talk a little bit about spontaneous fermentation, sour beers, and then I'm going to do a little bit of a chat through how to measure titratable acidity in your brewery at home. Once I've done that, I'm going to hand over to my colleague Molly through the modern technology, who's based on the east coast of the United States, and she's going to take over and she's going to talk about modern methods of souring and some things that we're doing in Lallemand to produce interesting products for sour beer. So today I'm going to talk about Lambic beers specifically, and these are obviously historical beers and styles that are brewed very much in a way which is similar to how beer would have been brewed in the past. So I think it's important, before I start to go through how Lambic specifically is produced, that we talk a little bit about how beer was produced in the past. So just look to how things used to be done. So in many respects, these things, this brewing was done in a manner in which is quite similar to what happens today. So worts would have been produced from malted barley using, for the most part in Europe, either decoction or single infusion mashing. They would have then been boiled as we do today, and then they would have been chilled as we do today. There are some particular intricacies with Lambic brewing in particular, and I'm going to go into that later. Sorry, I'm just hearing from a colleague that I might not be live. Let me just check. I do appear to be live, so let me know if you can't see me. So, as we got as far as saying beer was boiled as usual and chilled. Now, these chillers would have been open chillers, so they would have been open to the atmosphere. Following this, they would have been fermented, and then the beer would have been aged in wooden barrels, and it would have been blended to create the desired flavour profile prior to bottling or racking. Now, that's your kind of your standard brewing process, and as I've said, not much seems to have changed. But fermentation, how was that done? And this, in some respects, is quite similar to what we do today as well, with some beers. So in the case of, for instance, Flanders red ales, quite often you'd do back slopping. So you'd take the yeast from a previous batch and you'd add it to a new batch. And then the beer would ferment. In the case of Lambic brews, you would ferment spontaneously, and this would be due to wild microflora that would have flown in through the windows and infected your wort during the cooling process. The fermentations would have been mixed, and they would contain a mixture of yeast and bacteria. The results, it's fair to say, would probably have been inconsistent, and the beers would definitely have had a sour character. So I'm just going to share with you now some pictures of a brewery in the UK, which should come up. Now, this brewery is called Elgood's and Sons, and it's based in Suffolk, which is in the southeast region of the UK. And they very much resemble a brewery as a brewery would have been around the turn of the 19th century. So you can see the very old copper vessels. On the left-hand side here is the brew house. On the right-hand side is the hopback. Now, following boiling and following going through the hopback, they would have transferred the wort from the hopback into a cool ship. So I'll show you that picture now. On the left hand side here we have the cool ship, and on the right hand side we have a picture of a thing which is called a vertical fridge. So the beer would have been laid out in the cool ships, and it would have been allowed to cool due to the very, very thin layer of wort. They would have opened the windows at this time, and so microflora from outside the brewery would have come in and it would have rested upon the wort. Above the cool ship, you can see that in the ceiling there's some oak beams that are there, and it's thought that some of the microflora that appear in the brews at a later stage actually come from these beams. So that's the cool ship. The way the vertical fridge works is it's essentially almost like a backwards radiator, right? So you would have cold water running through the middle of a finger, and then the work would have cascaded into a trough above the finger and run along the outer sides, and then thus be cooled down. So in this particular brewery, these days they only have a cool ship and they're operating it not very frequently, so usually once or twice a year. But when I spoke to the head brewer when I went around this brewery, they actually used to run a cool ship and a vertical fridge at the same time. So they would have had the beer going along the cool ship, cooling down there, and then flowing through the floor and over the vertical fridge as well before making its way to the fermentation vessels. So you would actually have had almost a two-stage cooling process. Next slide I have is a picture of the cool ship actually being filled. So they actually cascade the wort into the cool ship from a height, and I can only assume this is to provide some degree of oxygenation during the process. So that's how things would have been done, and in some breweries around the world, this particular brewery in the UK and many in Belgium, things are still done in this way. But things obviously changed at some point, and most breweries don't now operate in this fashion. And if you listened to my talk on lager last week, you would have discovered this was down to several people. So the picture I have up now is a picture of Louis Pasteur. This is the French microbiologist who discovered that yeast was the causative agent in in alcoholic fermentation. So he discovered that yeast was the cause of fermentation, and it wasn't just happening on its own as was thought previously. Next we have this chap, that's Emil Christian Hansen. Now he was working at the Carlsberg laboratories and he did some pioneering work on purifying single-strain yeast cultures. And once he'd actually purified this single-strain culture, this actually being lager yeast in this particular case, he sent that yeast out all across Europe, and people started brewing with it, and they started brewing consistently, and they started repitching. So they started to have consistent fermentations using only one strain of yeast, and they wouldn't have had mixed fermentations in use any longer. Going forward from the 1900s, you would then also have had more hygienic systems being put in place, so plate heat exchangers, which obviously don't allow your wort to contact the air, and then really good, nice propagation systems as well. So we can see now how the brewing industry has changed from a very kind of old-fashioned and like a slightly hit and miss process to one these days that is very tightly controlled and doesn't really allow for any spontaneous fermentation at all. Now, there are still beers out there that are made in the old ways, and specifically today I'm going to talk about Lambic, but you could also talk about Flanders Red Ale and Berliner Weiss and Goes as well. And when I talk about Lambic, I'm talking about beers that are made in a particular region of Belgium, which is in this little yellow circle on my map here. It's between the Seine and the Dendre rivers, so the region are kind of around Brussels. And these beers they're interesting. There's things about them that are quite unique, both in the way they're fermented and in the way that they are produced prior to fermentation as well. So the grist is 60% malted barley and 40% white wheat, and the hops can be German or English heritage varieties, and they're aged for 2 to 3 years, and we'll see why they're aged for 2 to 3 years in the next few slides. In addition to this, they use a process called turbid mashing, and this is when you mash at a very high liquor to grist ratio, so you're talking about 8 to 1. And the worts are very dextrinous and they're turbid, so they're kind of milky. And that, again, much like the hops, actually is quite important for fermentation down the line. That dextrin profile is important. Now, the boiling process is very long, so that's 3 to 5 hours. Now, you remember in the last slide I told you that the liquor to grist ratio is very, very high, so 8 to 1. So because it's so high, you have an awful lot of liquor there, and you need to actually evaporate a lot of that to get a beer that's of any great strength. So that is the reason that you'd have a very long boil. Now the hopping levels are actually quite high, and that is because the alpha acids in the hops are very low because they've been aged for many, many years. And that's important as well because alpha acids within hops are antimicrobial. So if we think about a lambic beer, we think about a sour beer. That sourness primarily comes from gram-positive bacteria that will create lactic acid. And if there's a lot of alpha acids within the beer, then they will die off and they won't be able to do their work. So that is one of the reasons they use aged hops. Now, there's been quite a lot of work done over the years on the different stages of lambic fermentation, and it comes to pass that there are 3 distinct stages to the fermentation. There's an enteric stage. This is where enteric bacteria grow. Now, these are things that aren't actually very nice. They're like E. coli and things that will have kind of a nasty sulfur aroma. And it could be vegetal or fecal in their aromas. So not the nicest of bacteria. They're also quite intolerant to alcohol and pH, so as we'll see in the next few slides, they actually die off through fermentation. So you don't need to worry about them at the end in the end product. They're not going to be there any longer. Some of those vegetable flavors, though, are actually thought to be some of the flavors that are characteristic in lambic beers. So following the enteric stage, you have a stage when Saccharomyces microorganisms take over, so Saccharomyces yeasts. These can be lager yeast and they can be ale yeast as well. And they'll take over for about 2 weeks to 3 months. And they'll start to produce alcohol and they'll start to drop the pH. And this is important because it will kill off the enteric bacteria from the stage before. So following Saccharomyces, you then have an acidification stage. This will be where lactic acid bacteria take over and they start to create that characteristic lactic flavour that you see in spontaneous fermentations and lambics. So kind of overlapping with that and then following on from it, you have a Brettanomyces stage. Now these are yeasts that can break down dextrins. So if you remember before I talked about turbid mashing and I talked about how the lambic mashes produce a very, very turbid wort with lots and lots of long chain sugars in it. These Brettanomyces yeasts are going to start to break down those long chain sugars and into fermentable sugars, and then they're going to start to ferment them. So that extract level that you've got there is going to continue to drop, and your alcohol content is going to go up. At the same time, Brettanomyces yeasts tend to produce some quite interesting ester characters, and we'll see some of those in the following slide. Finally, at 8 months and beyond, you get oxidative yeasts. Now, these are film-forming yeasts that will sit on top of your fermentation, and they will produce interesting esters, but also, if they're given the chance, they'll produce quite a lot of acetic acid. So actually, they tend to be quite undesirable if they're allowed to take over. So you need to be quite careful with your spontaneous fermentations that you don't let too much oxygen in towards the end, because you will get quite a lot of acetic acid being produced. Now there is a very interesting graph, which I'm going to show you now, which has been reproduced in many texts over the years. The reference is at the top if you want to see the original paper, but this shows you kind of how a lambic fermentation progresses. So you have at the start the enteric phase here, and at this point this is when those enteric bacteria are taking hold and you're getting those vegetable and sulfur flavors being produced. You then get the Saccharomyces species starting out, and they will start to ferment and they'll start to produce ethanol. So that's this line here that you can see with my pen. That's alcohol being produced, and that's the Saccharomyces yeasts that are doing that. And that's going to be the Saccharomyces stage here. And that's about 2 weeks to 3 months. Next, you get the acidification stage, and that's going to be Pediococcus species for the most part that start to produce the lactic acid that you get in the fermentation. That's number 2 here, and you can see this is your lactic acid coming up here. Interestingly, these species of bacteria as well, they'll also produce a gel as they ferment, and you get this stage which is called thickness, where if you take the wort from the fermenter, it will actually appear to be ropey and kind of thick. And that stage actually does go away eventually, because you get, after your acidification stage, you get your Brettanomyces stage. Now, these Brettanomyces yeasts, not only will they eat dextrins, but they'll also start to chew through the slime that's being produced by the Pediococcus. They'll break it down, and they'll prevent that film from being there any longer. So you get that turbidity to disappear. I think line 3 is quite interesting. So this is one here. This is ethyl lactate. So this is an ester that's produced from ethanol, so alcohol, and lactic acid. The two react together, and this is mediated by yeast. So this happens intracellularly, and you can see that the line follows the line of lactic acid production quite neatly. So you're getting your lactic acid being converted into ethyl lactate, and that's quite an interesting flavour and quite prominent within lambic beers because it has a creamy kind of fruity taste to it. Number 4, pH. This line here is quite important at the start of fermentation because it kills off these enteric bacteria here, which we don't want. And you can see that it drops and it hits like a minimum about 12 months into fermentation. At that point, you start to get autolysis and stuff within the yeast, and you'll start to get a gradual increase in the pH towards the end of fermentation. Number 5 is just your real extract. So this is gravity. And you can see that it's coming down from the start, and it's a slow decline, and that's as those dextrins start to be eaten up by the Brettanomyces species towards the end. Now finally 6, and I think this is quite interesting for some people, 6 is acetic acid. So this is vinegar. So this isn't a flavour that you particularly want within a lambic beer, or really within many beers. It tends to have like be a small component of a Flanders red ale, bit of acetic character to it. But in a lambic fermentation, we see here that you get a little bit of production at the start, but it doesn't really increase too much, and that's deliberate. You don't really want that to happen. So there's been quite a lot of work on the actual bacteria that have been found within these lambic fermentations, and this is another paper that is really interesting to read. Again, reference at the top. And you can see at the start of this fermentation, you get quite a lot of the enteric bacteria and E. coli and Shigella being produced. That's these ones here. So the light blue and light green, and these aren't very nice. You know, even in a kind of normal environment, they'd probably give you some sort of food poisoning if you were to ingest them in any great numbers. As fermentation starts to progress, you're talking between 2 weeks and 3 months, you start to get these red ones being produced, the Hafnia. And those are bacteria that are actually associated with a lot of cheese making, so running cheeses, and are quite normal in a lambic fermentation. Interestingly, towards the end, so between 2 months and 24 months, so towards the end, kind of after these stages have progressed, the only bacteria these authors found within the fermentation was Pediococcus. So that is the dominant organism within a lambic fermentation. So all these orange ones here, that's Pediococcus. So next thing I'm going to do is some of the yeasts. So the same authors did a study looking at the yeasts within a lambic fermentation, and you can see here on the left-hand side of the graph, you have these pale blues and dark blues. Now the dark blue is actually Saccharomyces cerevisiae, so this is your normal ale yeast, and then the light blues are Saccharomyces pastorianus, so that's your lager yeasts. As the fermentation progresses, you then start to get the Brettanomyces coming through, and that's the kind of turquoise-coloured ones there, as well as these ones, Deboromyces hanaceae, and that's quite often found in soft cheeses as well. So you can see it's quite an interesting and mixed bag towards the end of fermentation. Now, a lot of these are oxidative yeast that probably don't add a great deal to the flavour profile, but probably do a little bit, and they're the ones that will also produce acetic acid if they're left to take over. So just going back to my PowerPoint now, we can see the dominant flavours within a lambic beer. So alcohol obviously is a dominant characteristic. It's warming and it's alcoholic. Lactic acid, again, produced by lactic acid bacteria. The Pediococcus are producing that. A bit of acetic acid from Acetobacter, but not a great deal. And then you have the butyric acids, the caprylic acids, by Brettanomyces species of yeast and the Saccharomyces species of yeast. These are generally thought of as bad in a brewery fermentation. Butyric tends to be thought of as kind of a vomity flavour, and caprylic is normally likened to a goaty flavour. But they're quite important acids to have within the mix because they also react intracellularly in yeast with alcohols, and they produce very interesting esters. So ethyl butyrate and ethyl caprylate are esters that kind of have an appley or a pineapple-y flavour to them. So they're quite important, both in their acid flavour, but also in the ester that they then produce. Volatile phenols, these are things like 4VG and 4EP. So that's your classic phenolic off flavour that you'll get in a Belgian beer, and then also your kind of horsey flavour that you'd get in a Brettanomyces beer. So again, important kind of flavours within the mix. Now that's all I really want to say about lambic fermentation. I'm going to go back to my webcam, just briefly, talk to you. Because I think it's important for us to talk about how many of the breweries today are doing mixed fermentation, not mixed fermentation, modern sour beers, so beers that are produced using non-spontaneous fermentation. So you're pitching an organism that will produce acidity in itself, and it will produce lactic acid. Now, a lot of brewers are following these fermentations, and they're following it using pH, which is one way of following these fermentations, but it may not be the best way. This is because whilst you can measure pH, you don't have a very good idea of the amount of lactic acid that is being produced, and the pH can be affected by other factors, for instance, how much the wort is buffered by the malt components. So I'm going to talk a little bit about how to do measurement of lactic acid, because I think it's important in a modern brew environment doing sour beers that you can measure titratable acidity as lactic acid. So the method that we're going to talk about is actually the ASBC recommended method for measuring lactic acid in a brewery fermentation, and it's based around the titration of a weak acid, in this case lactic acid, by a strong base, in this case sodium hydroxide. So I'm just going to show you a kind of picture of what I mean. So this is the base of the measurement. So in a aqueous solution of lactic acid, for instance, in this case, our beer is going to be our aqueous solution of lactic acid. We have the lactate ion, which is this here, and lactate loses a proton, which is this thing here, and it is what causes the acidity within your wort or within your beer. Now, if you want to measure that, we need to neutralize it, and we're going to do that by titrating it with a chemical called sodium hydroxide, which is this chemical here. And we're going to add sodium hydroxide, and in doing so, we're going to neutralize the lactic acid, and we're going to create a salt. That's going to be sodium lactate, which is this salt here. And we're going to create water, which is this chemical here. Now, as the titration progresses, what we find is that the pH will increase. And it will increase up to a point, and that point is 8.2, and that's called the equivalence point. And this is the point at which all of the lactic acid within the beer has been neutralized. And some of the sharp people amongst you might wonder why that pH is not 7, which is your normal neutral pH, and that is because as you titrate your lactic acid and you create the sodium lactate ion, you're actually going to have that ion be dissociated in solution. So you're going to have that sodium be separate from this oxygen atom here, which is negatively charged. And because that atom is negatively charged, it actually will cause the solution to be slightly basic, so slightly above neutral at pH 8.2. Now, I've got a few slides here that will just show you how the experiment progresses and what you'll need to do it. I had quite a lot of fun making these. I was going to try and make a video, but it appears that sort of level of video editing is beyond me. So here we go. It's quite easy, and you don't need a lot of equipment. So really what you need is a pH meter, pH buffers, a 100ml beaker to put your beer in, a magnetic stirrer, a burette, a measuring cylinder, and some beer to titrate. So it's a very easy process. So just going to go through that and show you what to do. And don't forget your personal protective equipment. You need glasses, you need gloves, and you need ideally a lab coat as well, because these aren't very nice chemicals. So first you need to measure your starting pH for your beer. In this case, I've got a beer that's 3.33%, pH isn't measured in percent. What am I talking about? 3.33 pH. You also need to measure the starting level of sodium hydroxide in your burette. So that's the start. The step 2 would be to titrate the beer. Oh, sorry, I'm not showing you. Here we go. Sorry, I missed that. I was showing you my my diagram still. So here we go. Measuring titratable acidity by lactic acid. So this is what you need, and I already spoke about that, so I'm not going to speak about it again, but this is what you need. You can see in the picture. You then measure your starting pH and the starting level of sodium hydroxide in your burette. And don't forget your personal protective equipment, as I said before, so goggles, gloves, and a lab coat, because they aren't very nice reagents. You'll then titrate the beer by adding sodium hydroxide, and you'll do it in 1.5 ml quantities, up to a pH of 7.6. And you want to do that whilst stirring with your magnetic stirrer relatively vigorously. If you see in this picture, I've actually overshot slightly, so I've gone up to 7.72, which isn't too bad, but you know, just do it slowly, and you won't end up doing that like me. Next step, you want to do it even slower, so you need to be letting really small amounts of sodium hydroxide into your beer, 0.15 ml at a time, up to pH 8.2, which, as we spoke about before, is the equivalence point at which point you've titrated all of the acid that is within the beer. That time I got it right, so I've said on the money. And then finally, you want to record your final pH and the final volume of lactic acid in your burette. So all very easy so far. You know, it's not a method that takes very long. It probably take you 5 minutes to do this in a brewery environment, and it's much more accurate than testing pH. So it's really quite a good way to go. Now you've got those results. You've got your measurements. You know the volume of lactic acid you had at the start. You know the volume of lactic acid you had at the end, and you know the volume of beer that you started with. So you can plug these into a very simple formula. It's a formula that's often used within breweries and within schools, high school chemistry. It's really easy, and that is volume 1 times concentration 1 equals volume 2 times concentration 2. And if you rearrange that for C, you can find C2, which is your concentration of lactic acid in moles, so your molarity of lactic acid. So in this case, you would do V1, which is the volume of sodium hydroxide you've used, times by the molarity of sodium hydroxide, which is 0.1. You would then divide it by V2, which is the volume of beer being titrated, which was 50 mils, and that would give you your amount of acidity, so your molarity of hydrogen ions in the solution. You would then multiply this result by 90 to represent your answer as grams per litre of lactic acid, which is a good way to do it. Now I'm getting to the end of my particular bit of the presentation here, so I'm going to go back to my webcam. And unfortunately, I think I've gone slightly over time, so I'm not sure there's going to be time for questions and answers before Molly comes on and starts to talk through her part. But before I do hand over, I'd like to draw your attention to the World Brewing Academy lectures, which I'm advertising on the screen above me. Now, this is a collaboration between the Domus Institute in Munich and the Siebel Academy in Chicago. They're really good. They're kind of single subject lectures, so you can sign up to single subject lectures and you can learn about a particular area of a brewery. So the one I always use is if you're a small brewery and you've bought a centrifuge and you don't know anything about centrifuges, you could sign up to the centrifuge lecture and then you could learn about centrifuges and you could then teach your staff about centrifuges. So I think they're really, really good, and we are advertising a 25% off deal, and that deal is going to be valid until Sunday the 19th of this month if you use the code LALSOUR25, which is on the screen above me on the webcam. Now, I'm going to go over to Facebook and I'm going to switch the feed to my colleague Molly on the east coast of the United States, and she's going to run through some modern souring techniques with you. There might be a slight lag between the two videos switching, so just be prepared for that, but it shouldn't be too long.
Hi, everybody. My name is Molly Browning. I am the East Coast Technical Sales Manager for Lambic Brewing, and today we're going to talk about how to produce really consistent sour beer. So, along with Andy's really great talk on spontaneous fermentation and lambic styles, this type of styles have a lot of mixed cultures in them. What we really want to do is look about what organisms are will help you create more consistent sour beers that you could replicate down the line. So let's get started. Let me go here. So we like to present which bug. It's going to be a discussion on which microorganism to choose for consistent sour beer making. Sort of sounds like a quiz show. And the answer is lactobacillus. So we are looking at this particular bacteria as it's one of the most versatile lactic acid producing bacteria out there. It is, you can find it in a wide variety of places in dairy, in fermented vegetables, and in wine. So one of the reasons why we really like lactobacillus in brewing is for this reason. It really does produce a cleaner lactic taste. Some describe it as tangy. And for this helps it be able to be create like a platform for many different styles of sour beer. So whether it be a fruited sour or a goza or Berliner Weiss, this bacteria can create a wide variety of sour beers in a really consistent manner. The reason it's so consistent is that it has the different species of lactobacillus have a specific temperature range in which they are active. So it's at these temperatures that they will produce more characteristics and acid. So we really want to dive in on to which temperatures are best for these certain species of lactobacillus. So to really identify where they can be active and where you can actually control how much lactic acid they produce. So one of the best ways to control how much lactic acid these bacteria produce is through kettle souring. So at Longmont, we looked at 5 different lactic acid bacteria strains, 2 plantarans, 2 Labrachii, a Helveticus, a brevis, and an acidophilus at 4 different temperatures. And we were really looking at the pH of each bacteria at these temperatures, how much lactic acid was produced, and how much acetic acid. For the time constraints of this presentation, we're really only going to dive onto 2 temperatures on this chart, the 30 degrees C or 86F and 40 degrees C or 104F. And we're really going to look at pH and lactic acid here. But if you would like more information, I can send you the slides in this presentation and really have a longer discussion if you wish. So we're going to look at holding these bacteria at 30 degrees C or 86F. This is really kind of what you would do if you were kettle souring your bacteria. So in a kettle sour, you are wanting your bacteria to express some flavor, but really just produce the acid. And we see here that these different bacteria will produce a certain amount of acid, or their pH will drop at a certain period of time. And what you're really noticing on this chart is the plantarum the 2 plantarums, and the brevis really start to drop their pH within 24 hours, and that continues on to 48. And around 48, they're pretty much there. They pretty much reach how much acid that they can produce at that time, as noted by pH. If we look at 40 degrees C, this is really kind of the tail end or the bookend for the plantarum. At 104F, they really don't produce much more lactic acid. The pH just really starts to bottom out there. So you kind of see that pH stop moving in 24 hours for the plantarum, and particularly for the Helveticus as well, is now a player in this at this temperature range. At 48 degrees, at 48 hours, you pretty much see it stop. So you kind of have an identifying marker saying, okay, well, we know, let's say I don't want to tie up my brew house for 48 hours. I know that at 104F, the Helveticus will produce, this much lactic acid, and the pH will drop to about 3.5 within 24 hours. So it really gives you a really good kind of marker for your production schedule, and also for how much pH or how much lactic acid and what your pH marker that you're shooting for, what you would find at that, like within that certain amount of time. If we look at lactic acid, so at 30 degrees C, so which is again 86F, 40 degrees C, which is 104, you're really seeing the plantarum and the Helveticus shoot up in lactic acid. So the plantarum A is our lactobacillus sour pitch. It's denoted by the blue line, the dark blue line, and then the Helveticus is the dark purple. So around 30 degrees C, you really see the plantarum A produce a lot of lactic acid. And at 40 degrees C, you're seeing the Helveticus produce a significant amount at that temperature. And we, in our taste panels, we found that we really liked the plantarum, which became our sour pitch, produces a lot of citrus and grapefruit and a lightly tart, lightly acidic flavor. For the Helveticus, the lemon, it produces more lemon, more citrus, sort of like a sweet and sour candy. And we also noted it had a higher perceived acidity, which was a really nice thing. So you can really sort of play around with these two different types of bacteria. The Helveticus might be better for if you're looking for a straight goza with no additional fruit. And the sour pitch, the plantarum, might be really useful if you were looking to add different types of fruit and add more complexity. So, along with bacteria, the other side of the coin when making sour beer is yeast. Yeast typically do not confer high degree of acidity to beer. Also, some yeasts tend to struggle in very acidic environments. So if you are trying to produce a really consistent sour beer, sometimes your yeast might struggle depending on your yeast strain. Wild yeast in particular, with Brettanomyces, for example, does not produce lactic acid unless it's used in conjunction with the bacteria, as you saw in the spontaneous fermentation examples. And the Lachantia species, it confers a degree of acidity, but with different flavor characteristics. So a little bit more funk. Those two types of strains might be unsuitable if you're looking to produce a really clean sour beer, or a really clean beer that's you just want to present an acidic taste to it, and possibly some fruit or something like that. So the gozas of Brettanomyces, for example, clean fruited sours. So what are your options? Well, if you're in the United States, you have this option. This is genetically engineered lactic acid producing yeast. We call it the Cerevisiae. It is a Saccharomyces cerevisiae. It has a wide fermentation range, and it will produce a significant amount of lactic acid, between 8 and 12 grams per liter. It will drop your pH also quite significantly. We tend to see around a pH of 3. Has a high attenuation level, has a really good ABV tolerance. And the sensory, it's just a very clean, very neutral yeast strain. And taste panelists have noted that there's no THP that they can detect, which you sometimes can see in kettle sours. So if you're in the United States, this is a GMO strain, So we are only able to sell this in the United States right now. This is an option for you. It is also really convenient to use in terms of production time, because you can just throw it in your fermenter and pretty much, walk away. If you're not in the United States, and something that we are adding to our sour portfolio, we will soon be adding a Lachantia strain. This is a very unique strain. It was a Lachantia. It was discovered by Dr. Matthew Farber at the University of Sciences in Philly in a graveyard. We will be launching this in the summer, so we will have more details and Dr. Farber to talk about it as well. But this strain will produce lactic acid and ethanol. As it is a wild yeast, it will also produce some of those funky characteristics that you will see with some wild yeast, but it will produce a really nice amount of lactic acid as well. It has a pretty wide fermentation range between 63 and 77 F is what we're looking at, and it will drop your pH to around 3.2 to 3.5. So that is all I have for you guys on how to produce really consistent sour beer. If you have any questions, or if you would like to discuss this any further, please feel free to email me. I'm available. And also, there is lectures for that. So please, if you would like to explore more about what we have to offer, Siebel has some really great lectures on different brewing subjects.